Recording. Good. Let's continue our lecture, and I hope I can finish chapter 7 before the final exam week. Otherwise, I need to extend 1 week, but I will try my best. Okay. Right. I will try my best to finish all the courses and exam within 16 weeks. Okay, I will try my best. So that means I don't have any more time to tell them a joke or any random stuff about my reason finding. Anyway, so let's continue our lecture. So last time we talked about the parallel axis theorem. Okay, so because during the proof we make use of the y bar in area integration, which is the x bar axis through the centroid equal to 0. Okay, because the bar, the green bar here, sorry. Well, which means that if you moving from the green bar, which means that you have a y bar dA can be ignored as a 0. Okay, but so you can ignore this and then you can obtain the result. However, if you start from other axis to move to here, you cannot apply this, or this term need to be in the green axis here, which is through the centroid. Okay, this is really important. And then we talk about normal stress in beams, that we talk about the location of the neutral axis, which is when we try to balance the force in x direction, and we found that it need to it generates this equation, and this equation indicating that the neutral axis locate the centroid of the section, okay, cross section. Okay, and then we talk about the moment and curvature relationship, because the curvature kappa is really difficult for us to measure, but the moment is easier for us because we apply the force and then we can plot the moment diagram in chapter 4. So moment is easier, but curvature is very difficult. So we want to replace curvature by moment. And then last time I forgot how to explain the negative. And thanks to these two students, because we need to make sure the m here, because we apply m, right, the positive m here, we need to make sure the m is positive. So when the y greater than 0, upper part, which means that the sigma x is get into the page, right? So which is a compression. So this is negative. So negative for negative become positive. So upper part generating positive moment. But y negative, y less than 0, which means that sigma x is out of the screen, which means that it's a tensile. So this is positive. So y become negative. Negative y, negative. So you have positive m. So this minus makes sure m in this area summing up together as positive. Okay, so this is the reason why we get the minus here. Thanks to the two students here. Thank you. And then after we summoned up all the bending moment in small area in this cross section, which will always equal to the total m in this section, in this correct cross section. And then we found that m equal to kappa EI, and that's how we replace kappa. The kappa can be m divided by EI. That's great. So m divided by EI we can replace the kappa. So sigma equal to minus my divided by I. Okay, so now we don't need to use curvature anymore, as long as we know the moment at that point. Good. Right, next one. So next one is the maximum stress at the cross-section. As you can see, the stress here is proportional to M, Y, and I, right? So in this section, M is fixed at that point, right? M is fixed. I is fixed. So the only thing we can find this, which makes the sigma become mixed, is only Y. Okay, so how can we find the stress, maximum stress, tensile compression, okay, compressive stress occurred in this section? Of course, the furthest Y from the origin, from the neutral axis. So either this one, either that one, right? Okay, so C1 is the furthest positive distance from the neutral axis. So this is C1. And the further negative distance is C2. So whatever the shape is, the far away, the farthest distant from the neutral axis will be the sigma max occurred, either compression, either tensile. Okay, so C1 and C2 are really important. So in mechanics of material, the author or the scientist give a name of that when sigma, I mean, when the Y becomes C1 or C2, we call this value as section moduli, 剖面魔术. Well, it's just a name. So the sigma 1 and sigma 2 is the maximum stress, either compression or tensile, and which is because the sigma 1 is substitute Y by C1, okay? And sigma 2 is substitute Y by C2. So sigma 1 MC1 minus divided by I, and we can say this one is S1. C1 over I is S1. C2 over I is S2. Okay, so S1 and S2 will be the section moduli. So you can just substitute the maximum. You see, regular rectangular beam with width B and height H. So you got I here, right? I here. And then your S must be substituted by half H, right? So you substitute your, so your I divide by half H, and then you can get S equal to BH squared divided by 6. So the section moduli actually is that how effective of this section or section can afford to against the moment. Okay, how effective. So typically we will choose higher section moduli because you will have higher stress, right? If you have higher section moduli, which means that for the same moment, you will have higher higher stress ability to hold it. OK， 好，总之就是要选高的剖面模数啦。剖面模数其实纯粹就是把你的 I 除上你最远的距离而已。要么最远是 C1， 要么最远是 C2， 上面跟下面就这样。好，那总之 C1 跟 C2 就会让stress 最大的地方，不管是压力还是拉力，看 M 是正还是负的啦。OK， 那接下来我们会使用到 That's it. Next one. Oh, this is really classic. This is classic. 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 Problem example of this chapter. So it wants us to derive sigma tension mix, sigma compression mix of this material, this beam. Okay, this beam. So this Q is 3.2 kN divided by M, and you can draw the V here. Sorry, you can draw V, and you can draw M. Okay. So now sigma T and sigma C is equal to minus my divided by I, right? We just derived this. So actually we don't need the V here. I don't go through how we get this two figure because I've done that in chapter 4, right? So you do this by yourself. And then we notice that the N has two maxima. One, N positive, which is 2.025 km dot M. And this is N negative, which is minus 3.6 kN times M. Okay? So you have two maxima M, right? So as you can see, because sigma equal to minus my divided by I, and of course you want to get the maximum, so either the y should be C2 or C1, right? And I, well, is fixed. Y is fixed because next page, we provide this cross-section area. Cross-section area is 不能讲么，英文没有么，a cap. It's a cake shape. Okay, 3 rectangular. Okay, so the I is fixed. Y become either C1 or C2. And next one will be the N. N will be the one which determine the sigma. Either it's a maximum tension or maximum stress, compression. We don't know. So these two stuff, these two things, you can see that the M positive make this place, well, here. Okay. Okay, so you can imagine that. Let me draw bigger. Okay, here. You can imagine that this place, da da da, and da da da. This cross section has the moment like positive, right? And this is negative. Okay, at that section, if you cut it through, and then you have M positive and N negative. Okay, that's right. So you can see that this cross section can have compression and tensile, and N negative can also induce compression and tensile. So which one is bigger? We don't know. We don't know. Of course, if your cross section is very symmetry, of course you know which one. But now this cross section is not symmetry, so it's not so straightforward. So that's why you need to calculate them. All right. So yeah, that's it. And I would like to draw a three-dimensional figure for this one. Okay. Otherwise, for the first time, maybe you don't understand what is going on, what is going on here. Okay. So here I'm going to draw a so of course this is X and Y side view. This is the side view. So I need to draw a is that called isotropic view? So actually, yeah. Okay. Not in real scale. It's just illustration. All right. So here and here. Wow, very difficult. Mm. Okay. So, wow, very difficult. So, hey.算了。嘿，嘿，嘿。All right. So this is M plus, M pos, and this is M negative. All right. And this is the shape. Anyway. Okay, so this is the three-dimensional figure that I hope it can help you to understand what does it what is going on here. So when you first time to encounter this when you first encounter the problem like this, maybe you cannot feel the shape. 哇，好难哦。哎，哒哒哒哒哒哒。 Right, that's it. Okay, I hope you can understand what I'm drawing. So, although it looks like a rectangular here, but go with the cross-section area draw in next page. Actually, you are encounter the problem like this one. Okay, this is a cat shape cross-section. So what you see here is this one. Okay, and then if you see the cross-section area, you end up in the next page. All right, and so this. This two cross-section area, this cross-section area is this one, and that cross-section area is for that one. All right, so this one has the positive M, and this one has that negative moment. All right， 看得懂吗？我已经尽全力画了，而且从小到大我没有看过老师画这张图给我看过，所以都要凭你想象力。Okay, I just trying to say that I have done my best. Okay. The only thing I didn't do is I draw a 3D computer graphic for you. Okay, but I hope this isotropic view can help you to understand the actual geometry that you are encountered in this example. All right. So now we are going to examine the maximal compressive and tensile stress in this cross-section and that cross-section. And then we compare which one is the greatest. That's the purpose of this problem. All right. 很难吧？要画图。我在想下一次如果要改课的话，我应该要把我刚刚真的用电脑3D 绘图把它画出来给大家看就好。但是我觉得，好了，下次再做了，我下次再做，我都没有，因为我为什么我要手画？因为这实在太难画了，太难制作了，所以我还反而用手画就好。虽然丑，但就不用在家里把3D 画出来，不然的话我叫学生把它画一下，助教叫助教把它画一下。Okay, maybe I just asked teaching assistant to use the 3D graphic tool to draw this for you. Maybe, yeah, maybe I don't know. Maybe it will be the best. All right, so I hope you can finish that. And I'm going to next one. Okay, the next page. Otherwise, I cannot stand for too long here. All right, next one. Next one, we're going to calculate neutral axis for this section. Okay, all the section in this beam section. Next one. Ta-da! Good. So now we're going to calculate neutral axis. How can we get this? We only know the so actually we are going to calculate the centroid for these combined areas, right? So firstly, because we're going to get the area, combined area centroid, so we need to set this is 1, this is 2, this is 3, area 1, 2, 3, okay? And then there is a most important step. Sorry. Area 2, area 3. Okay, so the most important thing is here. Setting origin. Okay, setting origin. we all know, we know the final answer should be somewhere around maybe here, right? We know that somewhere around here. So this will be our O later, but we don't know exact the distance. So we cannot use this one as our starting point. Now we are going to get a starting point. Where should we be? For me, I will set this point. I will say this is our starting point O plot. Okay? And of course, this is Y. But for me, well, it's okay. It is okay. So can I just randomly chosen my axis? Can I do that? Of course I can. Coordinate axis can be chosen randomly. Okay, as long as it fits your right hand rule. Okay, so the x and well y is okay. All we need to do is just setting a correct easy the starting point, easy for you to calculate. Okay, that's all right. So the reason why I choose that, I will tell you later, right? So I choose that in the top of the shape. So the y1 here, y1 equal to t over 2. So what is y1? Y1. Oh, sorry. Sorry, I forgot to tell you all the value. T equal to 12 mm. Okay, and the shape is 80. Is h equal to 80 mm. And of course, T is 12 mm. And the B here, the B here is 300 millimeter. Ooh. Okay. So this is given by the problem. All right. Right. So y1 equal to t over 2. So of course, t over 2, what's that? Is something here. Okay. Something here. Okay. Something here. Because the area's centroid, y1 over t over 2, which is 6 mm. So a1 equal to b minus 2t times t equal to 300 minus 2 times 12 and times 12, which is equal to 3312 mm square. So this is area 1. How about y2? y2 is y2 is h over 2, no problem, which is 40 mm. And area 2 equal to ht, at times 12, 960 mm squared. And area 3, similar to area 2. Okay, so now we are ready to get the centroid centroid coordinate. We are going to get the coordinate of O at the coordinate axis originating O prime. 我们会拿到 O 的坐标在什么坐标轴上 ？O prime 的坐标轴上。Okay, so now we're going to get that. Next one. So sigma yiai divided by sigma ai. Of course, this is the 6 times 3, 3, 1, 2 plus 2, 40, 960 divided by 3, 3, 1, 2 plus 2 times 960 equal to 18.48 millimeter. All right. So this one. So this is 18.48 millimeter, right? The O to the O plot. What is that? I guess you know why I put O plot at the top. Actually, this is C1. I believe you understand why I put this O plot at the top. Because whenever I get the centroid coordinates, and then it will be C1. Good. And C2 will be it will be and this is C2. Okay, what is C2? C2 is H minus C1 equal to 80 point minus 18.4A equal to 61.2 millimeter. Okay, so we got that. Good. So this is neutral axis. We done that. Good. So this is the first part of that. We set the neutral axis. Neutral axis is now here. This is Z. Okay. Right. Next one will be difficult because we are going to get I. So moment of inertia. Okay. Now, that's a little bit right. How to do that? So now here, moment of inertia. We need to move the centroid. Sorry. The moment of inertia at the central for the area 1 move to this line. Sorry, I should make it smaller. Okay, you can imagine that the moment is actually applied about this axis, neutral axis applied. So you can imagine moment from bottom to up, okay, or from the top to bottom. So it rotates about the neutral axis. So this axis need to be moved to this area axis need to be moved to the real area, real axis. And of course, this one, of course, need to be moved to here as well. So, well, please, because I put this to, right. Sorry, I will make it higher a bit. Okay. And I put here back. Right. So, sorry. just change a little bit position to make it easier to understand, easier to illustrate. And the other will be how to draw it. Right. So here. So this is the axis. This is the axis for area 2 and 3. Area 2 and 3 has its own axis, but we are not rotating about that. We need to move from there to the neutral axis. Okay? Well, sorry, I should say move from here to here. And here should be move from here to here. So you see the difference. So now we do it one area at a time. So IZ1 equal to IC1 parallel axis theorem plus A1 D1 squared. Okay, D1 is the distance between the red axis to the pink axis. Okay, 1 over 12, 300 minus 2 times 12, 3, sorry. Plus 3312 times 180.78 minus 6, right? Because the C1 from the top to the O is 18.48 and minus the half thickness of the area 1, 6, right? And then we can get 555,600 mm4. Okay, so we know that if this area 1, rotate about neutral axis, its new I will be 555,600. Okay, and next one. So we have IZ2 equal to IC2. I shouldn't use the same value, the same color. Let me change it later. Okay, I'm sorry for that. And plus A2. Let me see. Okay, I use. How about blue? I change this as blue. Okay, blue. I change this as blue. So A2, D2, 2. All right. So equal to 12, 80, 3 plus 6, 96, 960 times 40 minus 1.48, 2. So equal to 956,600 mm4. Of course, it will also equal to IZ3. Okay, because area 2 and 3 are the same. So this one, IZ, our answer, IZ1 plus IZ2 plus IZ3. Because I is the difficulty, how difficult of this area rotate about the axis. So summing up together, 2 2.469 times 10 to 6 millimeter power by 4. Okay, so now I guess you know why I said chapter 5 is the most difficult chapter in mechanics of material, because you can see that chapter 4 done, neural axis done, moment of inertia done. We still haven't touched stress, maximum stress, right? That's insane, right? It's crazy. 很难吧？我们做了那么久，我们连sigma都还没碰到。我们做 Chapter 4的图就是什么 shear and moment diagram 画完以后，找到最大值，然后我们还要处理它的 cross section。我们看到 cross section， 哇，是一个奇怪的 cross section， 我们就要开始去组合它，组合它的行星，然后接下来再组合它的 moment of inertia 惯性矩。哦，因为每一个现在这个 area 1, 2, 3都要 rotate， 就都要对着中性轴来走，所以你必须要把红色的移到粉红色，紫色的移到粉红色。哦，这真的很难哦，很辛苦。我们做那么久才要开始，我们才做好 M 跟 I， 我们还要 Y 啊，我们等一下下一页就是 Y。OK，so we just done M and Y, and then we are going to discuss Y in the next page. Very difficult. Right. iPad 跟 Apple Pencil 真的是可以把字写得还蛮好看的，那边自己称赞自己。Okay, next one. Right, next one will be Y. Okay, we talk about Y. So now I'm going to draw the side view. Side view. Okay. And Z toward you. Okay. I guess you understand this. This is the side view. And side view, the first one, this is side view, please. Don't treat that as a cross section. This is side view. All right. So now this we just cut pieces of the beam at that point. At that point is M positive. Okay. M positive. Positive. And of course, this is compression, right? And this is tensile. And this is tensile. And this is compression. Okay? And this is negative, M negative, minus, right? And of course, you can see this is the neutral axis. This is the neutral axis. And this one is C1, this one is C2, this one is C1, this one is C2. All right, let's substitute all the case. Sigma T in the M positive case, minus M positive C2 IZ, and sigma C equal to minus M cos C1 minus, divide by IZ. And yeah, this is my first hour. I will see you after 10 minutes. All right. So it's break now. I just finished this. You feel free to leave this classroom. Okay, that's it. I believe You understand what I'm talking about? That's it. See you later. If you have any questions, just come here. See what? Okay. So, okay. Right.
就是我简单简单的说讲，在二十，差不多到点，他是把那个让我这个是大概因为这里包括马上两个，三年考学变成不光你会在跟四十三三个人，主要是这个这个是去拿跟我三年这个书书很会有简单的，跟他会跟说是。我放的别的说的我都是，是对每个人，第二是那下面说是最高的说的，大概的情况就还有回来，所以任何我三年开始。
Wait. Welcome back. Let's continue. all right? Because we don't have time. Because I need to finish that before 17 week. Good. Right, let's go. Sigma t minus 2.025 times 10 to 3 times 61.52. Be careful, be careful. There will be a minus here because C2 will always be minus, right? Y is not the absolute value of the distance. It should be the coordinate number, coordinate value, all right? So be careful. .469 times 10 to 6 mm4 equal to 50.5 and BA. All right, so this is the first one, sigma t at m positive. And please allow me to do some shortcut. Okay, minus n positive C1. So I need to delete the C1. This is 18.48 equal to minus 15.2 m ha. All right. So at m positive, your compression sigma stress is minus 15.2 MPa. Next one, equal to the n negative. N negative is minus negative 3.6 times 10 to 3 times 18.48 C1, right? 2.469 times 10 to 6 millimeter 4 and equal to 26.9 m pa. All right, again, I will do some shortcut, copy and paste. Again, C2 need to be modified in this equation. So again, 61.52 with the minus in the front. And at the front, minus 89.8 m ha. Okay, so this is okay. This is the whole answer. And then, what is the sigma T maxima in this material, and what is the sigma C compression maxima in this material? Of course, you can immediately get that this is the sigma T max, this is sigma C max. So these two are the answer. Finally, the max. And this one is sigma C max. Okay, that's finally finished this. I guess this is, I believe the concept itself is not difficult. However, the calculation procedures are tedious. Okay, tedious 就是tedious 怎么讲？繁琐的。Okay, and really easy for you to make a mistake. So careful about that. 昨天我去那个录 podcast，你知道杨朝尧老师有做 podcast，那大家有看过吗？ 三是指 OK， 是指三则，很好。我只看过一个是杨朝老师自己的，你还有看过其他集吗？只有一集而已，不多，一集。那你觉得他制作的 quality 还行？不行，看起来不行。哦，那我要担心我昨天的那个成果。哦，没有啦，没有，我觉得这很难啦。就是你自己做一次你就知道，真的很难。那昨天这样听起来，我觉得访问我的那两位同学还蛮有水准的。对就是就是一开始的时候当然就是很紧张啊，就看稿啊什么，但是后来到最后就聊开了，然后就比较轻松这样。然后我就觉得，如果能用这样子的方式来赚钱，真的还不错哎，就一直聊天就好，聊，然后就可以就赚钱，很不错哎，对啊，但不知道有没有人听就是了。那没关系，我就觉得，哎，昨天录的感觉还蛮好玩的。然后他们会先给我访纲啊，然后我就想说，先把一些问题都想好，答案都先想好这样，然后就这样聊起来，我觉得还不错，蛮好玩的，是一个很特别的经验。Okay, so next one, continue. Design. Sorry, I just talked about the experience of recording the podcast done by Professor Yang's student. That's good. This is really a good experience for me. Right, next one. Design of beams for bending stress. So when you design a beam, you are choosing a enough section module. Okay, so typically we're going to reduce the weight. So we need to design a shape with sufficient enough cross-sectional moduling. Okay. Of course, you can see that because we typically has the moment in this condition. So the further the further uh, the further distant to the neutral axis, the greater the stress. So which means that if you want to save your material, you should have less material at central at neutral axis, but more material in the bottom and the top, right? So that's it. We need to have our material more areas away from the centroid, away from the neutral axis. Okay, so that maybe now you can guess why our bending beams are always looks like an I shape, because I is less in the middle, but more material at the top and the bottom. So this is actually the reason why. Okay, so now let's examine the efficiency of the shape of the cross section. This is the cross section. You see Z and Y and X is toward you. So this is cross section view. Okay, cross section view. Cross section view, we need to compare versus square and the circle. Okay, and the area has the area are the same. The value of the area are the same. Okay, so for example, you have a D here. So we have the radius is half D, right? So the half D has its area half D squared pi, right? And then we are going to get exactly the same area of the rectangular square. So our h is half D squared root pi. Okay, so if you times h and h square, and you can get exactly the same area number. of the circle. Okay, so this is half edge, of course. This is a half edge. Ugly. Half edge. Okay, so if we continue, we substitute the s squared section modularly h cube. Well, maybe you don't understand why, because I skipped the IC equal to BH3 divided by 12 divided by H divided by 2, because it's a C, right? So this is H3 over 6. So that's the reason why we have H3 over 6. And if we substitute this to the H, you can get this one, and you can get S squared equal to 0.1160 D cube. Okay, and how about circle? Circle pi d cube divided by 32. So you get 0.0982 D3. So you can compare this one and that one. Which one win? Square win. Ta-da. So the ability to against or against, right? Against bending. Okay, so 抗弯能力 against the bending, square is better than circle. So you sometimes if you cannot see the beam's cross section as I shape, sometimes you see square, right? But you never see any you never seen any shape the beam in circle, because this is not efficient. Of course, you have less material at the bottom and the top. This is not reasonable. Oh, sorry, I forgot to write down why is this. I divided by C. I divided by C is pi d4 divided by 64 divided by d divided by 2 by d3 divided by 32. So that's the reason why we have the value here. Okay, done. So circle is not a good choice for beam as a section, as a cross section. So now let's continue this topic. We're going to find the ideal cross section shape. I believe you know the answer, I shape. But what is the how do we get that? Okay, I believe this one is okay. And next one, ideal cross section shape. This is the ideal cross section. So neutral axis is here. Okay, neutral axis is here, and Y, and this is Z. Okay, again, this is cross-section view. Don't treat that as a side view. And of course, this is H. And this is A divided by 2. Okay, and well, this is A, this is B, and well, this is half edge. Right, so now let's continue. So let's calculate this the ideal. Okay, of course this is not gonna happen because there's no material connected. It will separate. But we're just saying that, oh, this is ideal in the dream. Okay, what will it be? So here is a A equal A divided by 2, AB, okay? And we need to let me take a look. Oh, we need to apply the parallel axis theorem. Okay, so the first one, AB3 divided by 12 plus ABH2 divided by 4. Okay, and now you have two area. So 2A divided by 12 and B squared plus A over 2 and 4H squared. Okay, so you can notice that we here H is we set in the middle, okay, in the middle here. So H2. We kind of neglecting the thickness of the blue area. We kind of treat the B is a really small, tiny, thin walls. Okay, so here we sort of neglecting the B square because this is a thin material, and if we do the square, it will become even smaller. Okay, so after that, we only have this one. Wow, I can say this one. Oh, I forgot to say this is parallel axis theorem. Okay, this one. Okay, so apply the parallel axis theorem. We calculate this ideal cross-section shape is AH squared over 4. And if we divide by half H, becomes 0.5 AH. Okay, so ideally, this is tiny material and separated into against the C1 and C2 stress. And in the middle, it's okay because they are relatively small. Okay, so this is ideal shape, but this is in a dream because this is not happen because there's no material connecting them. So at least we have a really tiny material as less as possible. So it's become I shape. So I shape cross-section area, it has S slightly lower than 0.5. It's kind of 0.35. Okay, so that's it. 好，总之就是这边我们在做一个很假设性的东西啊，这个 cross-section 根本不可能啊，因为中间没有连接。如果你有这个 cross-section，它早就飞走了，然后就是落下来了，它没有连起来。那这时候他们就说 ，OK， 我们尽可能的把 material 材料都把它放在 C1 跟 C2 的位置，那而且都是薄薄的，非常的叫什么？它的头哦，非常的想要弄得很节俭啊。然后呢，他就把这边的axis 移到正确的位置，这个移到正确的位置，所以他做了2次平行轴定理。做完以后，算出这一个理想的 I 是多少。那中间他做了一些也就是省略了哈，因为他说这个是很薄的一个板子，所以 B 的就是它的厚度很薄，所以你平方以后会变小，更小，所以就变成0了。OK，0， I forgot to write it。0， 然后呢，我们就得到这个式子，然后除以 S 等于0.5 AH。那如果但是不可能吧，所以现实生活中至少要有一个很窄的、很细的去连接起来。连接完以后，它就会稍微少一点点 S 0.3。OK，so that's it。 Next one. Another example. The example is kind of interesting. Okay, this example just want to tell you that the bending is not only for uh, up and down. I mean the like the floor, okay, but the beam can be treated or column can be treated as a beam. For example, a 水坝要怎么讲？忘记了，糟糕。Dam, right? Dam. Okay, 水坝 dam. Okay, the dam has a water pressure, so the water pressure will push the column of the wall of the dam. So we, and also because the water has the distributed load, right? The distributed load, the stress or the force will getting greater when the depth become deeper. Okay, so assume that the distributed load for the water pressure is Q naught. Okay, and then you can see the side view of the dam. Here is a this is a wall. Okay, this is a wall, and this one is some sort of column, but because of the bending, the loading, we can treat that as a beam as long as you rotate, twist your neck. Okay. Okay, so let's take a look. This is the problem B. The B here is the beam. Okay, and this is the height. Sorry, the height. Okay, and there, so the dam will be a long wall, right? Will have it will have a long wall. So which means that there are more than one beams. So this should be beam one and beam two. This is top view. See from the top. Okay, and the beam is designed as B. So you can see that this cross section area of the beam is square, and the span between each beam is small s. Okay, the reason why I said write down like this is because I don't want you to confuse with the cross section modular, sectional modularly, big S. Okay, later I will use that. So I use this small letter of the S. So let's continue. Right, so this should be the S. The S here should be this one. Okay. So let's continue. But before that, I need to draw another figure in the next page because I would like you to know the actual structure for this problem. Okay, so please remember this one and remember that one, and we are going to combine them together as an isotropic view of that, just like what I did in the previous example. Okay, so this is the wall. Okay, and this is the beam. Okay, this is the bin, and this is B1. This is and this is B, and this is B. Okay, and of course this is H. Right, and this is B2. B2. Okay, so you can imagine that this is all water here, right? This is all water. So now, actually, we can divide all the water by the bin. So you can imagine that one bin is responsible for this water volume. This is water volume 1. This is water volume 2. Okay, so, and this is the span. Span. Okay, so imagine that there are a lot of bins, B1, B2, B3, B4, B5, and this is all the water. And each bin responsible for such many water. Okay, to resist such many water. Okay, so this one is the stress we are going to derive. Okay, so some sort of you can think this is the S. So the Q norm. But actually, we are going to derive what is Q norm. Okay, the Q norm is this one. Okay, this one. What is Q norm? The Q norm will be the gamma equal to gamma, the water density, height of the water, and of course, this is one line. Q for one line is gamma h, but now you have an entire volume, so you need to times S. Okay, to considering the entire water volume for bin 1, and the bin volume for 2 is for B2. Okay, so Q naught equal to gamma HS. You need to consider, not only consider the one lines, you need to consider entire volume. OK， 好，就是啊，我们知道在做这条线，其实就是深度嘛，就是什么密度乘深度，就是它最下面的的力量，对不对？就压力嘛，但是不要忘了，就是其实这个 B1 它其实负责的水的体积其实是这么多，它不是只负责这一条线，它是负责一整颗这样子。那所以说，当然了，你可能会说，哎，老师其实是这样子，哎，一样的啊，你把它移到中间，一样的啊。总之，你从这边移到这里来啊，是一样的事情啊。那只是我这样比较好方便画。那所以说，这是第一个被冰1负责的水的力量，然后冰2在这里，然后就是 for 它这样 for 冰2。OK，so that's the in this page, I'm just going to tell you why the Q naught equal to gamma HS. So it's actually not really a typical question, typical example for chapter 5. But the reason why I choose this example is because that it actually tell us how to dealing with the problem we actually faced in the real world. OK， 虽然这一题不是很经典，其实上一题才是经典，就是第5章题目应该都要找上一题那样子。这一题其实就是有点特殊，但我觉得为什么选这一题，就是其实并不是只有想象中的像这样子啊，就是站在上面或者把东西放在上面。其实，在水坝啊或者这种有水的东西，其实也蛮有用的，因为它的水深的压力也会造成有 bending 的效果 ，distributed load 的效果。OK，so let's go back. If you can understand what I just taught, Q naught equal to gamma H S. Okay, so this one gamma is a density of water. Okay, and of course S is the span, and the entire Q naught is force, the units force divided by length, of course, because this is a distributed load, right? So the M mix, oh, sorry, I forgot to tell you introduce the requirement of this example. The requirement is that please find B minima. We need to design what is the B at least, which can handle this dam if the material sigma allowable is 8 MPa. So this material only can holding the sigma allowable 8 MPa. And we need to design the area of the beam, the cross-section area of beam. So we see M mix in this distributed load will be equal to Q naught H divided by 2 times H over 3. Why? Please refer to your chapter 4. Okay, so you imagine that if you have a being like this under the Q naught, and please calculate the mx. Okay, you can just draw the m moment diagram and you can get the mx value. Okay, and gamma h cube s divided by 6. So your s here is for sectional moduli. So here I will write down S. Okay, it's not span. That's the reason why I write down the small letter for the S. So this is M mix divided by sigma allowable. Okay, you need to get the sufficient cross-section moduli to handle this pressure. So now S for the square is B over 6. Do you remember that in page 223? Okay, in page 23 we just get the S square, right? We just obtain that, and equal to gamma H3 S6 divided by sigma allowable. Okay, and then our B cube equal to gamma S3 S divided by sigma allowable equal to gamma 9.81 times 10 to 3. and times 2, 3 times 0.8. Of course, this one is the density of the water. Okay? And 8.0 10 to 6 AMPa. So 0.007848 meter square, meter cube equal to B equal to 199 mn. Okay, so now you know how to design a column, a cross section of the column. OK， 其实这一题就是不太经典，它反而有点就是特别的 case，但我只觉得这蛮生活化的哦。那你可以看到，就是其实并不只是在天花板或是你的地板，好，它其实可以生活在它存在生活中，水库只要有水的部分，有那种 distributed load 的部分，其实它的墙面的柱子挡的柱子其实都是一个病。那所以就是给这个例子给大家看，然后如何去思考，就是说这个病是如何分担这些水的重量的。上礼拜四我做胃镜嘛，我们跟你讲，做吃低渣饮食很不舒服。我后来才发现，我不能吃这个，不能吃那个，让我非常的焦躁。原来我发现我是多么需要吃，就是吃了东西我就会开心这样，那不吃东西我就会非常的痛苦。那就过了2天以后，我去照胃镜嘛，而且你知道照胃镜是很好笑，就是我是做无痛的，所以他就会给你麻醉，然后就会让你呛掉，你知道吗？你有呛掉过？我也是没有，我也是第一次麻醉，然后我还真的蛮呛的。你知道我那时候注射麻醉的时候，因为我就想说，我常被听到就是说注射麻醉就是忽然就，哎，然后下一秒你就醒来了哈，就听我就想到好，我来试试看，然后他就开始注射嘛，然后我开始算1、2、3、4，我在心里算6，然后就算到27，然后就下一个阶段了这样，然后就结束，然后就27，然后我为什么知道我自己很僵，你知道吗？因为通常你在自己心里想的是27，你如果是正常人，你不会跟护士讲说，我刚刚算到27，但我一醒来我就说，哎，我刚刚算到27了，然后他们说好好好，然后但是我那时候都没有觉得怎么样，我就觉得说，我我做了一个实验，我做了一个实验呢，然后我算到27，好酷哦。然后我醒来我就蛮因为我很僵的，然后我就蛮开心的就跟他分享，我算到27，然后结束以后，然后他就把我送出去嘛，然后我就坐在那边，我后来就越想越不对劲，然后我干嘛跟他分享这个27这个数字？嗯，果然是真的僵掉这样。好，讲完了，这是我昨天的，不是昨天，上礼拜四的那种状况。然后做完以后不是无痛吗？对不对？然后我就回家嘛，回到家我就肚子痛了2天，那种痛就是觉得说有人就是打你一拳的感觉，不是那种拉肚子痛，也不是，反正就是很痛。然后我就在想，他一定就是在 mess up 我的肠子，mess up 我的胃，就拿那个管不是去胃镜吗？就这样戳，然后什么，因为我会觉得哇，我的肚子好像被殴打的感觉，然后我觉得这个胃镜实在是一个很痛苦的一个检查，但是又不得不检查，因为年纪到了。然后很好笑，我跟罗老师真的是一个真的是很有缘啊。他说他也去做胃镜，他最近也做胃镜，然后他说他是做就是没有麻醉的，然后他就是当下很痛，但是后来就比较好一点点这样。他就说那为什么我会那么痛？是因为当下我没有感觉啊，所以医生就在那边就随便弄，然后他就好了。这是 mess up 我的东西，我的器官这样，很痛苦。好，anyway，就是上礼拜真的是一个很痛。 然后抽血，其实我很怕抽血，其实我很怕针，但是身为一个男生，我就觉得我不能这样丢脸，然后就只好这样，就抽血，好烦哦。好，讲完了，下一个 ，next one，just talk about the physical checkout I done last week. Yeah, nothing interesting. Okay, so here is a bar, uh, has a point load P at the tip, and the A and the B will be is the the A the B is the diameter of the area A, point A and point B, and then dB and over dA equal to 2, the ratio between them. And they want this problem want us to find sigma B at the fixed support. Okay, this is actually not correct. We need to get sigma B makes at the fixed support. So because you can imagine that the sigma normal stress of this point B can be many answers, right? Because this could become 0 and become bigger away from the central neural axis. So you need to give the maxima to let us to give the actual value. So here will be the maxima occurred, right? The top or the bottom. Okay. So this is the sigma B mix. And the second point, the second item is sigma mix. Oh, so which means that the maxima is not necessarily obtained here. Okay, so this is not always correct. Okay. Right. So let's continue. Right. Let's continue. So what will it be? Firstly, we need to get the chapter 4 things. RB. Okay. You need to determine what is RB, right? Then you need to determine the shear and moment diagram. So I will just give you the answer, okay? Because I have done that in chapter 4. So this is actually this problem as chapter 4 looks like. Just the one line with the fixed end and the point load at the P at the front, and also the V here, V0, and the answer should be looks like that. Should looks like that. Like this one, and like that one. Okay, and this is minus px. All right. So I don't go through this because I have told you, okay, in chapter 4. So please do your done by yourself. So now this is minus px. So here will be a m. Okay, the m is minus px. Minus px. Right, so this is all chapter 4 part. Okay. Next one, I'm going to determine the chapter 5 part. The chapter 5 part, sometimes when you talk about sigma mix, maybe you will think you think the sigma mix occurred at this place because m here is the greatest. However, don't forget, the cross-section area is changing. You have the greatest M, but you also has greatest cross-section area. So this is actually the balance. Okay, so we need to find the sigma max maybe somewhere in between. Okay, because the cross-section area is also changed. So you cannot directly get M max here, M negative max here. Okay, so now let's go chapter 5 stuff. Chapter 5 stuff, we need to get because the cross-section area is changing, right? So we need to get the section moduli as a function of x. So before that, we need to, again, very similar to what we done before. We need to get this is just illustration. It's not in scale, all right? So here, this one is dA divided by 2. And this is x. And this is d x divided by 2. Okay, and this is dB divided by 2. Okay, so based on this one, we saw this shape many times, right? Remember in chapter 2 and 3? So dx divided by 2 minus dA divided by 2 divide x. Similar triangle. dB divided by 2 minus dA divided by 2 L. Okay, so the dx equal to dA plus dB minus dA times x divided by L. So S x equal to pi dx cubed divided by 32. 32. dA 讲到 CAN 这件事情，大家的酒品好不好？大家知道自己的，大家有了解自己吗？听我朋友说，我喝醉的时候，我就开始讲英文，我就开始讲英文，然后对，就讲英文，然后唠英文，然后很有趣的事情就是我如果用英文讲话的话，我会变得比较有礼貌，所以我酒品还算不错，可能比本人还要有礼貌。Okay, sigma mix should be mx divided by sx. So px is the m mix. Okay. As you can see, the minus px is actually not the value, it's a function. So when x equal to 0, the m is 0. Okay, so this is actually a line. So this is a function. And divide by pi 32. Wow. I should have copied that. BB minus dA. Okay, so I will continue to solve these questions, solve this example tomorrow morning. Okay, so I will see you later. See you tomorrow. All right, so if you have any questions so far, just let me know. Thank you. Bye-bye. 但是超过这时间，超过这个时间就不能再要喽。没问题，有没有问题？谢谢各位。然后那第九张会跑，我再传给你。好，别忘了关这个。